All right. Hello, everyone. My name is Salim Nassi. I'm part of the Biomedia Group at Mohammed bin Zayed University of Artificial Intelligence. I participated at this challenge along with my team members, Arsen, Dr. Nauman Saeed, and Dr. Mohammed Yaqub. We are presenting our multitask approach using weak supervision for improved ultrasound measurements. To be brief in this challenge summary, I'll proceed with the contributions and then follow out with the methodology and results. We experimented to find the optimal training methods that is best suitable for our multitask objective. And we showed that generating synthetic labels and utilizing weak supervision can help in cases where there's a lack of label data. Our model architecture is exactly the same as the baseline provided. However, we extended the classification head here to have an extra layer, and our model characteristics have 35 million parameters and 260 million flops. As for the training dataset given by the organizers, it was consisting of 434 videos with 512 by 512 resolution, where 25,000 frames were positive, and a subset of it was labeled, summing to 2,500 labeled images. The negative frame count was 31,450. Our pre-processing consisted of getting those frames extracted from the videos and saving them as PyTorch tensors. As the dataset contained 22,000 positive frames with no masks, we made use that most of the frames have little variations within the videos. So training a model to produce synthetic masks shouldn't be hard and should produce decent masks. We trained an NN unit using five-fold cross-validation with 1,000 epoch per fold, and then we assembled those models to get the labeled frames to produce around 22,000 pseudo labels, and then we added them to our training set. The validation set is the same set provided with 40 videos, same resolution as training. And then we discarded two potentially corrupted videos, which might have corrupted label mappings. The set contained 1,500 positive frames and 1,200 negative frames. 38 frames of those had the corresponding masks after discarding the two. We used additional data sets which were public. We evaluate our model at first and then like as a test sets, and then use them part of the training for the final model. The BSFH dataset contained 4,000 positive images of 256 by 256, along with their masks, and then we resized them to 512 by 512. The other dataset, the GNU IFM dataset, consisted of 78 videos, which I think it has a huge overlap with our training set. It initially contained 6,000 frames from 51 patients with 1,000 by 1,200 resolution. We ignored the overlapping patients using the date timestamps from the names. And since the dataset had more classes than we are interested in, we labeled any class that is not having both structures as negative, and included the frames which has both structures into our positive set. This left us with 882 negative frames and 2,900 positive frames, which again we resized to 512 by 512. During the training, we initially experimented with simple summation of the classification and segmentation losses. This always produced oval validation classification matrix. So later we found out that dynamic loss scaling worked better here. Simply, this is dynamically changing the trade-off between classification and segmentation during training. So the total loss is the weight of the classification loss multiplied by classification loss and added with the weight of the segmentation loss multiplied by segmentation loss. So the weights here are calculated based on the current iteration losses Specifically, classification weight is equal to classification loss divided by the sum of both losses, the classification and segmentation losses. Also, it is also it's safe to assume that the synthetic masks can be unreliable. So we split the segmentation loss further, where now it is a sum of the loss of the original labeled images plus a weak supervision weight multiplied by the loss calculated from synthetic labels. Having these synthetic labels increase the positive class, which helps the class imbalance issue. However, we further employed a weighted random sampler to manage this imbalance. The weighted random sampler is a probabilistic one, so we calculate the sampling probabilities based on sampling weights of 0.5 for the negative images, 0.25 and 0.25 for both the labeled and the synthetic images. For the loss calculations, or the loss functions, we used binary cross entropy for classification and settled with dice focal loss for the segmentation task. As for our augmentation strategies, we employ 3 levels of augmentations to improve the model robustness. We used complex augmentations, which included aggressive transformations such as affine, elastic deformations, grid distortions, color jitter, Gaussian noise, sharpening, and contrast adjustments. Medium augmentations applied a milder version of these complex settings, which focused on moderate geometric and color variation. The minimal augmentations included slight adjustments like minor rotations, translations, and brightness contrast changes to maintain the augmentation variability while preserving the structural integrity. In our experiments, we used mixed precision training with PyTorch scaler for a stable gradient scaling. We also mainly used MONAI, and for our model evaluation, we used the accuracy F1 score, area under the curve, and dice score. The initial experiments were performed basically to guide us in choosing the augmentation setting to go with, and of course the weak supervision weight. So in these experiments, we used the following configuration. We trained for 30 books using small learning rates of 1e minus 3 with an Adam optimizer and varying batch sizes of 20 and 12. So in these experiments, we conducted a total of 5 experiments. And for the complex, medium, and minimal augmentations, we can see from the tables in the early training, the classification and the dice scores are generally performing better with more complex augmentations. Then we explored if the synthetic labels were aiding in our training or not. So we did experiments using varying weak supervision weight. And the conclusion here is basically the higher the weak supervision produce the better segmentation results, especially. It didn't affect the classification a lot. In the final set of experiments, we used the schedule-free optimizer from Meta, and we are now setting the final seeds for our final training strategy. We trained 5 models using varying learning rates. Actually, we trained a bit more than that, but some of them just diverged during training. Generally, we can see that 3e minus 3 and 2e minus 4 learning rates produced the best balance between the evaluation metrics. But an important conclusion here that steered our final training strategy is that we can see the validation area under the curve metric generally implied more consistent results on the 2 test sets here. The 2 test sets are the additional public data sets here. As for our final training strategy, we added the 2 public data sets into our final model training and kept the validation as a held out set. We trained 4 models using 4 different learning rates with a batch size of 20. The weak supervision here is 0.9 as concluded by previous experiments and also complex augmentations. We also decided to first train the segmentation task until the model has reached around 96% in trained die score. And then we kickstart the multitask training to include the classification. This was mainly done to prevent any overfitting for the classification, since for segmentation it took longer to reach good results. We chose the best model based on a combined metric of 0.7 of die score plus 0.3 of AUC. This choice is mainly due to the final task being dependent on the segmentation results. As for our testing results compared to the challenge baseline is shown here. So basically some highlights here: 66% on accuracy, so a 14% improvement, and 86.4 die score, which is a 6.3% improvement. And generally, we can see higher classification metrics and lower ASD, HD values, which can reflect more precise segmentations. As for the biometry measurements, we got a 9 absolute difference in angle of progression and 11.55 absolute difference in head symphysis distance. And for the post-processing, we have done the following. So we retained separate class masks for each of the structures. For the PS mask, we just took the largest connected component. And for the fetal head mask, we first took the largest connected component. Then we did some erosion with 5x5 elliptical kernel and 7 iterations to remove any small protrusions. Then we took the largest component again and filled any holes. And lastly, we dilated the mask back with the same kernel, and we did 7 iterations to restore the size. We can see the segmentation qualitative results here. Those are some of the success cases. We can see good localization of the PS here and somewhat good on the fetal head. These are also some of the more challenging cases in validation. We can notice here some poor pubic symphysis localization and extra segmented regions from both classes. And we also did some test time augmentations, but we did not report the results in the paper, nor it was considered for final ranking. What we noticed here is generally we see considerable improvements, especially in the pubic symphysis class. So it had more of a better localization and angle between the two endpoints. We can see in some of the cases here after doing the test time augmentation. And here this had an extra region here. So when you do the final task, these can aid better on the calculations, since it will have a better PS, which is crucial for task 3 to get these two endpoints. We also after submitting the challenge, we also tried it on the classification task, and using our submitted model, we saw 5% accuracy improvement on the validation set. So there is more work to be done here. I think it can help to be used here. And this is all from our side. Much thanks to the organizers and participants. We hope that we can provide much better models for this important clinical task. Also, best of luck to all the participating teams. If you have any questions, please feel free to ask. Hello?
Okay. Good morning. Good evening, guys. Let me introduce myself first. My name is Gantje from the University of Sydney, and over the next 20 minutes, I will introduce the 4 parts, increase the backgrounds, where I give you the information about the limitations from from this kind of modality data sets. And also we will give what kind of challenges we found from these data sets. And after that, based on this limitation and challenges, we will give the corresponding methods. And following by this part, we also designed experiments because we are trying to prove our methods is work on these data sets and also have the good, robust performance on each test. And finally, we also will give the convolution over these challenges. So for the first part, thanks for Dr. Bai and also how to organize this kind of really meaningful challenges. And these challenges, the target is to design the really good and efficient networks, trying to achieve the solid and robust performance on the three different tasks, such as the classification, segmentation, and the biological measurements. And over these challenges, so we only use the data set from the organization, provided by the organization. And over these data sets have the two different class, including the non-standard and the standard. And this really large data sets, we think is enough for those three different separate tasks. And in this data set also have about 2,575 frames labeled in these data sets. Regards evolutions, for the classifications, we will the challenges require us to use the accuracy F1 score and also the Marshall correlations coefficients and the AUC to evaluate the classification's performance. As for the segmentation, also the Brady Commerce evaluation methods that is similarity to coefficient, but also HD and also the ASDs used to measurement the performance for the segmentation. But finally, for the biometric measurements, we only have the two parameters need to be detected. It's about AOP and also the HSD. And this image is all of the tasks over these challenges. So first, we need to identify each frame from the video to classify which one is standard or not standard. And then we need to do the segmentation tasks based on the standard plan to identify the regions for the PS and also the FH. And then we need to do the measurement based on the segmentation results to get the AOP and also the HSD. So we first had to analyze these data sets, and we identified a few challenges. So first is definitely the noise. You can see the left side here. We also use the box to label the noise. As such, we use the red box to label out the noise. And also, we also label the task-related features. And we can see here, we can observe from the left images, we can see here, the task-related features actually is really hard to be identified if you don't have enough experiences on the ultrasound imaging. So based on it, we are trying to use the histogram equalization, trying to enhance the features stored in the image, in the ultrasound image. And we discovered after we use this enhancement the methods, the task-related features also to be enhanced and more reasonable. And we definitely think they can kind of to help the deep learning models to capture the task-related features better. But we also found another province. The noise features it also be enhanced by the histogram equalization. And these kind of things also is this also the new challenges is create after we use the histogram equalization, because after we use this kind of methods, the noise will be enhanced and make it featured to be more difficult to be distinguished between with the text delay feature and the noise feature. This also makes some difficult to the deep learning training tasks. So based on those challenges, we designed the methods. This is our methods called MTSTN. This is a totally new framework on to process the video data sets. So first of all, the data will be first to processed by the wavelet converts this kind of the structure to integrate the wavelet transform with and the two-dimensional convolution, because the two-dimensional convolutions have the really good capability to extract some information such as edge and such as surface features from the image. After we process the image, we will feed the data into the video 3 transformer. This is kind of the framework to capture the local, global, and temporal features. And after that, we will use the structure like the units to decode the information was encoded by the video 3 transformer, and then we will send the corresponding features into the 3 different heads to finish the three different tasks. So based on the method we assumed, we designed this experiment trying to analyze our methods can work and can get the robust performance in this kind of data sets. So the first thing is we test our models in the classification performance, and our accuracy performance is more higher than the baselines, because we got 78%, and for the F1 score, MCC and IUGC and are better than the baselines. And you also can see the right size image. This is what we use the grid cam to visualize the layer in our modules, and we can see our modules actually capture the task relays features. And for the segmentation and the biometrics, our model also present pretty good results than the baselines, and you can see the right side of the result prediction. And our module in the segmentation tasks, our predictions is more closer than to the ground truth. And after that, our endpoints predictions is also better. Is also close to the ground truth points. And finally, our modules in the bioinformation measurements, our errors in this kind of task is also lower than the baselines. So for the conclusion, over these challenges, we developed a totally new framework trying to fuse the global and local and temporal features in the ultrasound image, and our framework is also overperformed than the baselines, in the each tasks and more. The modules are also calculated pretty fast because we also tested the loops. It's only about 100 turns, and I think this can help the patient to work in the real time the surgery operations and also the baby burns. And in the future work, we are trying to improve our this baselines because we do the faster work now already in our base work, and we test the new modules in the validation data sets. The classification accuracy can reach about 88%, and also the segmentation, the performance also increase a lot. So in the future, we are trying to give the more reliable and also the robust performance modules in the future on the ultrasound imaging fields. And finally, also pretty thank you again to Dr. Bai and also Zihao to organize this pretty meaningful challenges, and also looking forward to more ideas to discuss. Thank you.
Technology of China. Our team is VSCBIC. We have taken part in all three tasks of the IUGC challenge, namely the classification of standard plans, the segmentation task, and the measurement task. We have utilized the data sets of both the IUGC challenge and the former FH-PH-AOP challenge. The entire dataset had been split into a training dataset and a test set in a ratio of 4:1. For task 1, we evaluated many deep neural networks for the classification of standard plans, such as DNNet, SubNet, and some transform networks like Performer and the Pyramid Vision Transformer and architecture. For training, we adopted the ADAM-W optimizer with an initial linear rate of 0.0004, and the poly scheduler was adopted. Each experiment ran for 100 epochs with a batch size of 6/4. Regarding pre-processing, we resized each image to 256 by 256. Each image is normalized to range of from 0 to 1. The argumentation, we adopt the auto-argument, and we use the cross-entropy loss for the task. For inverse stage, we horizontally flip each image and took the average of the model's prediction as the final output. Finally, we select ResNet as the final classification model with a parameter count of 21.29 million bytes and loops of 4. This is the parameters on the CPU device. For task 2, we also evaluated many classical deep models for the segmentation of field head and public symphysys, like UNet and DeepLab V3. For pre-processing, the images were zero scored, which is different from our solution for task 1. Additionally, the loss function is a combination of cross-entropy loss and depth loss. And for test, we use the TDA For the inference stage, we flipped each image both horizontally and vertically, and the average was set to be the final prediction. Finally, we chose Deep Lab V3 as the segmentation network. The network has 23.83 million bytes with flows of 89.94G for tensor with such a shape on the CPU device. And for task 3, two clinical parameters are required to calculate, namely the AOP and the HSD. The two parameters are calculated automatically on Chinese websites, and the results of our method in the validation phase are shown in table 3. That's all for our solution. Thank you for your listening.
Yeah, we're one group from the Oxford Machine Learning Neuroimaging Lab, based here in the United Kingdom. So we were a bit of a larger group, I guess. So we had Jay, myself, Mark, Hoda, Christian, Anna, Hugo, Maddie, and Nicola working on it. I think motivations are the same as for the most of you. So we all participated in the same challenge. Just to give you a quick overview of the few key innovations we came up with. So first of all, we used sparse sampling to mitigate class imbalance, and also to make the training overall a bit more robust. We then used several models for both the classification and the segmentation tasks, which were then ensembling into our final prediction. And for the last task, we used ellipse fitting to make the biometry measurements more robust. This is an overview over how we subdivided the 3 tasks. The first task was pretty straightforward, the classification tasks. So we used the batch of frames, which we then fed into our models and averaged results to basically filter out whatever we classified as a standard plane. Only the standard planes were then fed into task 2, which were again processed by multiple models and averaged to end up with a segmentation, again, only for those we identified as standard planes. And then segmentation was directly used to measure the distance between the fetal head and the pubic symphysis, and ellipse fitting was used to determine the angle of progression. Let's have a close look at our models, which we used and trained. So as you can see here, we used both negative and positive frames to train, and then also later to test our classification network. We used a cross-entropy loss for our classification network. Every plane we identify as being a standard plane were then fed into our segmentation network, loosely based on unit structures. More details on that later, which then gave us our final predicted segmentation. For the segmentation network, we used a combined noise and cross-entropy loss. The classification models we used, we tried to use a wide variety of different models. So we had 2 VGG models of different sizes, which we used. We had 2, again, of different sizes, 2 ResNets. We had 1 wide ResNet, a dense net, 2 efficient nets, and a conv next, also with quite a bit of variety in their number of model parameters. The segmentation models we used, as I already said, were mostly based on unit structure. So we used a vanilla usenet as well as UNet++. We also used DeepNet v3 and an MANet. So let's have a look on how well our models performed on task 1. So as you can see here, or sorry, just to walk you through this table, quickly. So in bold, the best results are highlighted. The second best are underlined. And for star, we are marking those models which were trained both using the pre-trained weights provided by PyTorch, and we also trained them from scratch. For the rest, we trained using the pre-trained weights. As you can see here, for us, the VGG 11 performed the best with respect to accuracy, and denseness for the other measures. So those are some examples of correct predictions, and also correct predictions of identified standard planes as well as non-standard planes. And in the bottom row, you can see some of the incorrectly predicted frames. I think the biggest innovation here was that we used a different, or what we found, which resulted in the greatest improvement, was that we very sparsely sampled the training data set to encounter the class imbalance between positive and negative frames. So let's have a look at the second task. Again, the structure and the highlights in the table are the same as for task 1. So we can see that UNet++ combined with VGG performed the best across most measurements. Those are the results of our segmentations for task 2 of the on the validation dataset provided by the organizers of this challenge. As you can see here, we are we have quite compact structures, which we're ultimately looking for, which is quite nice. We'll also try to have a look on task 3. So especially what we found that sometimes, especially in like quite hard cases to segment, we found that with some extensions to our compact structures. So in order to get rid of it, we came up with an algorithm which fits an ellipse to both the pubic symphysis and the fetal head. And we found that helps a lot with reducing errors, and especially it helps a lot with getting more accurate measures for the angle of progression. So those are the results on the validation dataset we were provided with by the organizers of the challenge. So across all the measures, we performed quite well. Naturally, we saw a drop in performance for the testing dataset. So those are the results the organizers sent us a couple of days ago. But still, we ended up with an accuracy of 0.67 and an F1 score almost at point.
Security Smart, and I am Zhonghui Sha. To tackle this challenge, our team has proposed a U-shaped hybrid network for fetal head and pubic symphysis segmentation, which we named DSSA UNet. We will introduce our method from these aspects. In this challenge, we select standard planes from ultrasound videos or images because standard planes contain complete information. On these standard planes, we segment the pubic symphysis and fetal head. Based on segmentation results, we calculate 2 key parameters, AOP and HSD, to ensure a smooth delivery process. Next, we will provide a detailed explanation of the methods we used. Our team has attempted to use transformer, which can model long-range dependence to address this challenge. However, standard self-attention mechanism brings a high computational burden. To alleviate this issue, we adopt a novel content-aware sparse attention mechanism proposed in our network, dual sparse selection attention. Specifically, we divide the feature map into regions. For this query, we calculate the relevance between this region and all other regions. Note that we perform an averaging operation, calculating the mean of all tokens in a region to obtain QR and KR. Next, we perform matrix multiplication operation between QR and all KR to get AR. Using a top K1 operation, we select the K1 regions which most relevant to the query region, and we can record their index in IR. The process of selection of the region level can quickly filter out unrelated tokens. Assuming that we select these two regions, then we gather the tokens within them to facilitate subsequent matrix multiplication. We can obtain KG and VG. Since this region contains 4 tokens, we can compute their attention scores. Through matrix multiplication, we obtain AT using a top K2. Using a top K2 operation, we select the tokens with the highest correlation to the query token for each row of AT. Further refining the selection to find the most relevant features. Based on the corresponding index, we retrieval the corresponding values from VG, obtain VGG. Finally, we reshape VGG and AT, perform a matrix multiplication, and obtain the new tokens. In summary, our DSSA involves selection processes at both regional and token level. And it has the following characteristics: reduce computational complexity, remove noise features, and allocate attention more precisely. In this challenge, we propose DSSA UNet, a CNN transformer hybrid network for fetal head and pubic symphysis segmentation. We stack varying numbers of DSSA blocks at each stage to form a symmetric U-shaped encoder-decoder segmentation network. Specifically, we designed a 4-stage pyramid-shaped backbone for the U-shaped segmentation network. After each stage, we perform patch merging for downsampling. Because the deep layer contains richer semantic information, so we adopt a pyramid pooling module (PPM) to integrate multi-scale semantic information. Subsequent channels are fixed to CD, aim to reduce the computational burdens. Additionally, we introduce skip connections with convolution operations and multi-scale built-in modules. 1x1 convolution can integrate channel information and reduce the number of channels, thereby reducing computational complexity. And we perform multi-scale feature fusion on the feature maps output by decoder. Unsample them to the same resolution, concate them along the channel dimension, and then apply a 1x1 convolution. Finally, after unsampling and 3x3 convolution, we obtain the segmentation results. When performing classification tasks, we utilize the shadow layers from segmentation network, aims to reduce the computational burden of the network and accelerate model convenience. Specifically, we freeze the parameters of these two shared layers and train only the subsequent layers, which significantly reduce the computational burden. Ultimately, we carefully designed the code to integrate both classification and segmentation tasks into a single file, making it convenient for the testing phase. Next, we will introduce the specific implementation details of the experiments. All experiments are conducted on a single NVIDIA GeForce RTX 3090 with 24 gigabytes of memory. And we uniformly use a DMW optimizer and trim for 200 epochs with a fixed resolution of 256 times 256. And we set initial learning rate to 0.0001. The batch size is 80 for classification and 30 for segmentation. Additionally, we employing some data augmentation strategies, such as rotation flipping and contrast adjustment. Notably, the backbone network uses weights pre-trained at the ImageNet dataset. Finally, we will present our experimental results. For the classification task, we split all samples into training and validation sets in an 8:2 ratio. The validation set results are shown in table 1. We can see the accuracy is 95.69 and AUC metric is 99.21. For the segmentation task, we validate the model on the official validation set and automatically calculate two key parameters, AOP and HSD. We have also counted the model's parameters and flops. The parameter is 29.25 and the flops is 7.15. Thanks to the design of DSSA and the four-stage pyramid, DSSA UNet achieves excellent segmentation results with minimal resources. Additionally, we visualize the segmentation results, and it's clear that we accurately segment each category, closely matching the ground truth.
Of ways, so I'm kind of hard carrying this project. So I'll just jump right in. So we had two tasks, classification and segmentation. And for classification, we just decided to go for ResNet. We think this is a solid choice. So there is 25 million parameters, and we train it for 1.5 days or maybe 2 days on my friend's gaming PC. I'm not really sure how many flops it had. I think 6.7 teraflops, like he told me. So if you're not familiar with the model structure, here it is. It's a little complicated, but there is a lot of convolutional layers. So if you're interested, you better Google it. And for the loss function, we just decided to go with cross entropy, but this loss function result in a loss. I think the classification part of our solution is absolutely a failure because we failed to work with data imbalances. So it's basically predicting negative every time. But I failed to recognize it on time. So I think this is my mistake. And it kind of wasn't really obvious from graphs. So I actually thank you for all the presentation because I was learning how you guys deal with that kind of problems. Next, my slides. Yeah, so this is the result. We didn't really get good results in a classification problem. For a segmentation problem, I decided to go with LinkNet. So if you're not familiar with LinkNet, it's a pretty lightweight model, and there is a few reasons, because I thought that it's more useful to use lightweight model in like a real world scenario with like very slow computers. And also another reason is just my potato computer cannot train anything harder than that. So it has 11.5 million parameters. I was training it one day, and I kind of approximated the teraflops of my computer, but just for the comparisons, I think it can run Elden Ring on maximum. So I think this is about right. So as you can see, this model structure, we were using mobile network encoder that is pre-trained on the ResNet model, on ResNet weights, and it actually did somewhat good. So yeah, we use the combination of Dyson cross entropy loss from the baseline model code. So I didn't really change it, maybe some little tweaks, but we kind of got a really fine accuracy for such a small model with die coefficient of 0.78 on the train. No, it was validation. Yeah, I'm sorry. It was the validation. And after that, so if you can see that our model was very clumsy, so I was trying to make it, basically to summarize everything that I have here, I was trying to make it more smooth and fit an ellipse inside. And for the task 3, I just used the CFE2 library to extract the contour, and I deleted the inside thing. I used some GitHub code that I found on the internet to fit the ellipse and just use some vector calculus. And for the results, here are results. I think it's pretty terrible, but it was a nice experience. So thank you for attention. If you have questions, you're not welcome to ask me because I'll probably fail to answer that. But thanks for organizers. I was the one who was asking a lot of stupid questions. Thank you for your patience. That's it.
Distinguished apples and schools, good day. We are the HHL Hotpot team from Chongqing Normal University. I'm Zicheng Hu, the president for our team, and today I will be representing our reporter on the topic application of multispectral attention mechanism in ultrasound image classification and segmentation. In our classification task, we use SENet as the backbone network, which learn to automatically capture the importance of each feature channel, enhancing the response to key features while suppressing those less relevant to the task. Additionally, we incorporate a multispectral attention mechanism, enabling the network to capture diverse information carried by different frequency components and flexible selected frequencies to extract features at various scales. After being proceeded by the multispectral attention layers and combined with residual contexts, the feature maps retain the algorithm information while enhancing the response to user feature. By extracting information from different frequency components for each channel, we further improve the feature extraction capability, helping the model achieve more accurate classification in complex scenarios. This is my segment network. In our segment task, we use the U-Nest encoder-decoder architecture, incorporating pyramid polling to extract multi-scale features. Also, this multi-level polling offers strong robustness to the small deformations of the PS and FS targets in ultrasound images. Similarly, The application of a multispectral attention mechanism enhances the model's ability to capture information for different frequency components. The features are then passed through the shifter block, which embed the respective field via shifter operations, keeping richer contextual information and improve overall performance. This is my pre-pro setting. First, we extract video frame and save them as PT files in the NEC and post phones. Next, we convert the tensor data to NumPy arrays, normalize them, and transform them to the PNG files for classification. Then we load the image and its mask, generating a classification mask using pixel virus, and apply transformation to enhance data diversity. Finally, we normalize the image to the between 0 and 1 range, convert it to CHW format, and return to process image mask and image ID for segmentation. Our train process and learning strategy are as follows. First, the model is set to training model. Then each batch of training data is proceeded to computer outputs and loss. If deep supervision is enabled, the range loss is calculated. Then gradings are zeroed and back prediction updates the model parameters. After training, the model switch to Aliva model. While teaching data is used to capture outputs and loss, and metrics like IOU and dice coefficient are recorded. Finally, the learning rate is adjusted dynamically, and early stopping is used for improve the promotion and prevent overfitting. The loss function we used is die loss, C loss, and curve importing die loss. The curve inter dice loss is combined dice loss and C loss. The second line is number of primers is segment task, and the second line is the number of